Hello and welcome to the Einstein Mathematics program, which is a high performance mathematics program for top achieving students in primary school mathematics. This session here is appropriate to age levels roughly 9 to 11 and perhaps grades 4 to 5. And this is going to be a preview of lecture number 1 in our program. So we would like you to watch this carefully to see what's coming up next in the actual lecture. So we will start the lecture with the discussion of the Polya system of problem solving. George Polya was a famous mathematician from Hungary, and he wrote a book called How to Solve It. There's the title here, How to Solve It, published in the year 1959, very difficult to find. But in his book, he gave a large number of techniques that one could try out in order to make some progress in solving problems. And we will discuss them carefully in the lecture. But these are guess and check, draw a diagram, picture, or a sketch, make use of a table, and then look for a pattern. Fine. And another technique one could look at is to make a simpler version of the same problem. This might help one to make some progress on solving it. So these are some ideas we're going to discuss in the course of our program as it unfolds. Now, to help you to understand how it works, let's take a simple example of this type. Now, in this example, what we have is a 3 by 3 square. We call it a 3 by 3 square because there's 3 blocks on the side and 3 blocks going downwards. So 3 by 3, that makes 9 blocks altogether. And this shape is actually made up of matchsticks. The question is, how many matchsticks are making them up? Well, 1 is there, 2, 3, 4, 5, 6, 7, 8, 9. Carry on counting. How many matchsticks are there in a 3 by 3 square? Now, once you work that out, we're going to ask you the more difficult problem. What if you were to construct a 20 by 20 square? How many matchsticks will there be then? Do you think it'll help to draw such a big picture? Well, maybe, but it's quite complicated and difficult to count that way. How about a 100 by 100 square? You must agree that that will be impossible to actually draw and count from there, right? Or I could make it worse, a million by million square. These are certainly very difficult numbers to work with, so they're so big. However, in the lecture, we will teach you how we can solve those big problems, but by using very simple mathematical reasoning. All right, so you tune in for the lecture accordingly. Now, let's consider, so what you can do is fill in your answers in these blank spaces and compare them with the discussion that we will have during the actual lecture. Another problem that we are going to be discussing is this famous magic square problem. I'm quite sure you heard of this problem before. It's a famous problem, as I said, but it has many surprises. The problem is to place the numbers 1 to 9 in the square so that the total of any column, row, or diagonal is exactly 15. Well, normally we wouldn't tell you what the total is, but we are so kind in this example that we have told you that you must aim for a total of 15. So you can place the numbers anyhow you like. 1, 2, 3, 4, 5, 6, 7, 8, 9. And now you find the totals. And let's see if you can get a total of 15. Okay, so how can we get a total of 15? So if I add sideways, 5 plus 3 plus 4, that's 8 plus 4, 12. So that's going to give me 12. 1 plus 2 is 3 plus 7 is 10. 15 plus 8 is 23. So none of these work. So I'm also supposed to get these ones working downwards and the diagonals. These diagonals here as well. So in the example I've given, none of them work. But there are examples that work. So we would like you to find the examples that work. And in fact, the challenge is not just to find the examples. The question is, how many different ways are there? And that's where you'll find a very surprising result that we will discuss in lecture number 1. Then you can move on to Jugs' example. example of Jughead. Jughead is near a river. He has a 3-liter jug and a 5-liter jug, as you see here. How can he get 2 liters of water? I'm not going to discuss this with you now because I think you have an idea of how this works. You can try that out on your own. Move on to number plates. How many different number plates can you make with these letters and numbers? Suppose you have KL456. Now, which city could be KL? Think about it. Anyway, how many different number plates can you make with these letters? You may not repeat a letter or number in the same number plate. Also, most places, letters come first. So let us assume in this problem that letters come first. In other words, you can't mix the L and the K into the numbers, like 4KL56 is not allowed. But KL564 is allowed. Okay, and you could even have LK645. How many can you make up like this altogether? How many combinations can you think up? Finally, we look at match tricks. Just like our 3x3 square at the beginning of the lecture, we have again a case where we have, this time it's a 3x3 square again. So 1, 2, 3, 4, 5, 6, etc. Now, these are matchsticks. Can you take away 4 matchsticks and leave 2 complete squares? Important point is complete. So you cannot have a square like that with a matchstick dangling out there, or one on this side here. That's not complete. There must be 2 complete squares. Likewise, we would like you to try out the remaining ones. Take away 8 matchsticks, leave 5 squares. Right, and move on to the last 2. Take away 7 matchsticks, leave 8 squares behind. Right? You always start off with a 3x3 pattern at the beginning and then try to solve the problem as you go along. Fine, so these will be the problems that we will be discussing in lecture number 1. I look forward to meeting you there. See you then for lecture number 1.